Oh my god. Why is it so long? Like 24 pages, Alan. Oh, I'm gonna die. It's okay. So the title is Modular Cellular Soft Robotic Material for Continuous Morphing Across Reconfigurable Topologies. What is topologies? By who? Alan? I don't know your middle name. Alan. Alan N. Fab Pratap. I cannot say the last one. I don't know. Okay, from the Department of Mechanical Engineering, Worcester Polytechnic. I'm gonna die. Institute. Okay, I don't care about that part. Okay. Abstract. Many soft robotic platforms are fixed in size and topology at fabrication, limiting task-dependent reconfiguration. Here we introduce a modular soft robotic material composed of a single what the fuck is this word? Composed of a single monolithically 3D printed, pneumatically actuated cellular unit with integrated actuation and modular connectivity. Repeated assembly of this unit into different topologies produces continuous morphing structures that generate controlled 3D shape change through bias guided out of plane buckling from simple in-plane cell expansion. Oh, in planar arrays? What is that word? What does it mean? The material functions as a continuous shape display capable of generating multiple surface features, including contour geometries, large overhangs, and object interaction. Reconfiguring the same unit into cylindrical topologies yields continuum style bending and grasping. What the fuck am I doing? How do you say this word? Peristal locomotion and self-rolling locomotion. Am I going local? Together, these results establish a scalable cellular architecture in which reconfiguration of a simple repeated building block produces diverse soft robotic morphologies and functions. It's 3 minutes, and I just finished the abstract. Not even one page. Contributions at a glance. Introduction of a single monolithically 3D printed, pneumatically actuated cellular unit with integrated actuation, and modular connectivity. Demonstration of controlled 3D shape generation through bias guided out plane buckling from simple in-plane cell expansion. Demonstration of shape display, grasping, and locomotion from the same repeated cellular unit through topological reconfiguration. 1. Introduction. Oh my god. I don't know if I can do it fast. Okay, let's try. Soft robots are often designed as task-specific bodies whose size, connectivity, and overall morphology are largely fixed once fabricated. When the required behavior, scale, or body plan changes, adaptation therefore commonly requires redesign and refabrication rather than reconfiguration of an existing system. A more scalable alternative is a soft robotic material built from repeated units that can be manufactured once and then assembled into different topologies as functional domains change. Here, we use the term soft robotic material in the sense of a material like robotic architecture built from repeated functional units, where distributed local behavior gives rise to system-level morphing and function. Such an approach could preserve the continuous, compliant deformation enabled by soft matter while reducing reliance on bespoke robot bodies for each new task. Realizing this vision remains difficult because a reconfigurable soft robotic material must simultaneously support continuous shape change, distributed actuation, scalable fabrication, and topology level reassembly. Existing soft surface and skin-like architectures can produce smooth, continuous deformation and conformal robotic functionality, but their oversize and connectivity are typically fixed after fabrication. I'm lost. Modular robotic systems can enable reconfiguration, but many rely on rigid multi-component units that limit compliance and scalable continuous morphing. Other repeated unit architectures can generate reconfigurable geometries, yet remain largely constrained to two-dimensional deformation modes. Related shape display platforms, including pin-based and membrane-based systems, can render programmable surface geometries, but they are typically oriented toward planar surface display rather than reconfigurable soft robot bodies, and are often limited to predominantly normal direction displacement or slower reconstruction dynamics. I'm dying. I'm gonna do 2 pages. What is this? Soft tubular and continuum robotic systems, by contrast, can achieve bending, crisping, and other embodied behaviors relevant to cylindrical morphologies. Peristaltic and rolling locomotion have likewise been demonstrated in soft body system. However, this cylindrical and locomoting system are typically developed as task-specific robot morphologies rather than as a reconfigurable repeated unit materials that can be reorganized across distinct topologies. Taken together, these examples underscore how difficult it remains to unify scalable fabrication, continuous morphing, local actuation, and topological reconfiguration in a single repeated architecture. A promising route toward such a system I'm gonna need some water is to encode shape-generating behavior directly into geometry of a tessellated cell. Prior work on out-of-plane buckling and architected materials has shown that geometry can be used to produce mechanically programmed deformation, stiffening, and stable deployed states, although these systems often lack the local controllability needed for multifunctional robotic behavior. We therefore sought a repeated cellular unit that is manufacturable, pneumatically actuated, tessellatable, and able to convert simple actuation into control out-of-plane morphology. The Ceres linkage provides an attractive basis for this goal. Am I right? Because its lateral expansion is accompanied by leg rotation and geometry-dependent mechanical response, suggesting a route to directional biasing and shape retention in larger assemblies. In addition, Ceres-based systems have been explored in reconfigurable material arrays, self-folding modular machine, and millimeter scale articulated system relevant to medical tools, indicating that the geometry is well suited for repeated cellular construction. Here we introduce a soft robotic material built from a single monolithically 3D printed, pneumatically actuated cellular unit with integrated actuation and modular connectivity. Repeated assembly of this unit into different topologies produces continuous morphing structures that generate controlled three-dimensional shape change through bias-guided out-of-plane buckling from simple in-plane cell expansion. In planar assemblies, the repeated unit supports continuous surface morphing, multi feature shape display, overhang formation, and object interaction. Reconfiguring the same unit into cylindrical topologies yields continuum-style bending, grasping, peristaltic locomotion, and self-rolling locomotion. I'm local right now, okay? I'm going local. By using one manufacturable cellular architecture as the basis for multiple larger-scale robotic functions, rather than assigning a separate mechanism to each task. This work establishes a reconfigurable soft robotic material that begins to close the gap between scalable fabrication and multifunctional reconfiguration. The end. Thank you.